So what we learned in this first class, which I forgot to record, was basically that anything we might possibly do at all is to probe nature up to a largest possible energy scale. And we'll call this the ultraviolet cutoff. That's where experiment goes. And since experiments gets all the way up to here, you can say nothing. Hic sunt leones. Well, not really. You might think, I want to find out whether the theory is still valid, say here. So this is my energy. So, you can still make a prediction and hope that, say, in one generation, the experimental threshold will go up. And then you'll be able to check, in which case, this point will enter the horizon of science. And it's still science making a prediction for an experiment to come. Obviously, it is not physics making a prediction for an experiment that will never come. That's another thing. Not necessarily a bad thing. It's mathematics, applied mathematics, whatever you want to call it, mathematical physics, physical mathematics. But it's not physics, because making a prediction for something that can never be tested is outside scientific method. So what we learned is that whatever you do with a physical description, you have to come with a model, which generally comes with a Hamiltonian or a Lagrangian or whatever you want to call it, and a scale. And the scale is the ultraviolet cutoff. And you say, I'm going to make prediction that I trust up to this scale. So you see, by starting off looking at the simplest possible problem, a small, very tiny variation of the Schrodinger equation of the hydrogen atom, we discover that we can address the following question. What does it mean? What does it take to make a theoretical physics model? Well, it takes an equation of motion, if you say, or something that tells you what are the descriptor of the theory and how they change in time. For sake of simplicity, let's call it a Hamiltonian. But maybe it's not, maybe your theory is formulated different necessarily. It doesn't have to be formulated in terms of a Hamiltonian. Maybe your theory doesn't have an Hamiltonian and it's something else. I don't know, a stochastic process or whatever you want. In the future, we'll discover that Hamiltonian description is fluid. Doesn't matter. Okay? You need a Hamiltonian and you need a scale, a UV scale. So let's review what we've done in physics so far. I don't know, you studied the hydrogen atom. Fine. The hydrogen atom is valid as long as you're looking at predictions that are with an accuracy that is with a spatial resolution that is larger than the size of the nucleus, right? Otherwise, you enter the realm of nuclear physics, which is not in the Hamiltonian, right? So your cutoff of your theory will be somewhere the Armstrong and the Fermi scale. Say 10, 20 Fermi scale? Fine. Let's move on. Let's do nuclear physics. Fine. You put more ingredients, you get a different Hamiltonian, and then you have a typical, in this case, the typical energy scale. In nuclear physics, you have like protons that are point-like, but protons have a Fermi size. So now you have, you can discover that nuclear physics holds as long as you have energy momentum of the order 1 over the Fermi in units of h bar c, which corresponds, say, to 200 MeV, roughly speaking. And if you go past 200 MeV, you're going to go look inside the nucleus and discover there are quarks and gluons. And you enter the realm of hadronic physics that you're very happy you write QCD, which is the fundamental theory of quark and gluons. And all you're doing, you're shifting above your scale. Now your theory is valid over a much larger scale. And the big problem with this Russian doll sort of construction is that at some point you run out of experimental resolution. And that's why people, we said the other time, built LHC. They built LHC because they couldn't falsify the theory all the way to the cutoff. So basically, they built a model that was called the standard model. The natural cutoff of the model, the highest scale where the model was tested, was the, say, 1 tera electron volt or 100 giga electron volt. So up to this scale, all the predictions of the model were proven completely right. There was no discrepancy. Very good. So people naturally asked the question, are they going to still true above this scale? Let's find out. They built the LHC, and what the LHC did was to move this above to the, say, 100 teravolt, maybe 10 teravolt scale or something like that. So they shifted it to a new cutoff, higher in energy. Unfortunately, still perfect agreement. Nothing new popped up. So whatever new there is, it must be up here. And so on and so forth. So theoretical physics, making a theory corresponds to finding the right degrees of freedom, right the Hamiltonian from the right degrees of freedom, that are compatible within a scale. So there's nothing wrong with Newton's theory is not wrong, is a perfect theory up to the nanometer scale, or if you want, the milli-electron volt scale. Anything that goes below those energy or distance scales, perfectly well described by nuclear theory, by Newton's theory. It's not a wrong theory, it's the right theory with that cutoff. But if you rise that cutoff, you're going to get more resolution, you're going to dive into the quantum realm. As you go down into the quantum realm, you are Ant-Man now. And when you are in the quantum realm, you discover that, you feel like you had an LSD trip. Nothing looks like classical mechanics anymore. So there's new physics. You have to start again, write a new Hamiltonian, and push forward. That's the first big lesson of this course. There's no theory without a cutoff. It looks, if you were to say this 30 years ago, people would not be completely agreeing. Now, I would say 99% of the community, 95% of the community completely agrees with this standpoint. There's no fundamental theory of everything. There's only the best theory possible until the scale that we have been resolving today. It's giving up a lot. It's breaking your child's dream of discovering the universe. Fine, time to grow up. We've been through that. But you see, and when I say grow up, I'm not talking about you, I'm talking about the scientists. Because in the last 10 years, when I was a student of your age, the real cutting edge science was string theory. Everybody wanted to do string theory. Until at around 10,010, it was completely clear that there is no way to validate string theory experimentally. No way. Or falsify it. So many people abandon string theory and try to get effective theories for low energy, whatever it is, or do something else. But some people began to push forward the idea that for physics to have a scientific value, you don't need validation with experiment. Mathematical consistency is good enough. And this, of course, is, to me at least, I think that Galileo is sort of revolting in his grave, and I think it contradicts the very essence of what it means to be scientists. But there are a minority of people who believe that, and I listen to them. I have nothing against listening to those people, but I would say nowadays people have understood this very clearly. Over the last 30 years, at least, it has propagated to become the way we think about science. Effective theory with an inside better effective theory, with another inside better effective theory, like with Rush and Dole, and you go from effective theory to effective theory. You never go from effective theory to theory of everything. After all, if you really think that the standard model is the theory of everything, it means that, what a coincidence, physics stops at the scale where we run out of energy in the accelerator. And there's nothing more from there to infinity, to the Planck scale. That's a coincidence if there's no physics precisely from the scale where you stop looking. Cannot be, right? I mean, you're not so naive. Okay, I think I made a big point. You don't need to agree with me. You're people. This is the common view now. I'm not giving you my personal view. I would say this is widespread view in science, but it didn't become accepted without a huge discussion for a few decades. So, feel free to be uncomfortable with it and to say it open. I mean, I like disagreeing students, okay? But what I'm trying to say is, as you get close to the frontier of science, you begin challenging what you gave for granted. And that's one of those situations. I would take a 5 minutes break, and then we go try to, learn from this lesson and use what we learned from this lesson. Oh, now it's almost 6 o'clock. I see. There's no point to make a break now. If you agree, I'll go to 6:15 and stop, okay?
Okay.
Can you guys
It's
take it?
fine.
Prof, se mi permette,
Sure.
purtroppo io la devo salutare perché ho un impegno e anzi ne approfitterei per chiedere se a lei va bene anche chiaramente alla classe, se riusciamo ad anticipare la lezione di martedì.
A che ora? Beh, va bene, devo sentire la classe, però. Allora, facciamo così. Ci sono due opzioni qui. Se facessimo fino alle 6, tu potresti?
Sì, entro le 6 esatte sarebbe per me
Allora,
perfetto.
facciamo, siccome altre persone hanno un corso prima e gli orari sono pazzi in questo momento, allora facciamo un commitment che io parto, faccio un'ora e mezza diretta e finisco alle 6, va bene?
Va bene, per me.
Perché se no, se voi vi mettete d'accordo, io sono disposto a cambiare orario, ma la vedo molto dura perché ho partecipato a questo orario. E
certo.
se noi partiamo... Ok, va bene.
Va bene, io la saluto, prof.
Va bene.
Buona serata.
Buona serata. Quindi, guys, let's go back. So now we learned this. The delta function was not good enough. In my theory, I was putting more assumptions that I was aware of. I was formulating a theory that was valid to infinity energy scales, and I could not do it. So now we're going to go back and start over with this idea in mind. And this is what renormalization theory is all about. Do things the right way, keeping in mind that experiments have finite resolution. So the first step of renormalization is get rid of sectors of the theory. Or let's not be so technical. Exclude from the theory UV, all degrees of freedom with energy above the cutoff. I can say nothing about them. My theory has a Hamiltonian cutoff, and whatever is there above the cutoff, I don't want it in my theory. Because if I have it in my theory, I have to say what's its dynamics, and I cannot do this. There's no way I can make any statement about that. Clear? So the first thing I want to do, I want to get rid of it. Okay, how do I do that? This first step has a name. It's called regularization. Those who have done quantum field theory have done regularization. They put a cutoff on a momentum loop integral, but I didn't realize the physical implication of that. They look, maybe they did. I was saying, normally in quantum field theory courses, this is taught as a mathematical trick. Then you reabsorb it into the charge and you do all these very annoying things that make you very uncomfortable, right? Reabsorbing infinite things. There's no need of thinking that in that awkward way. Let's think physics. And the physics says there's a cutoff. I can say nothing about the cutoff because I have no experimental information. So let me throw away anything that is about the cutoff. How do I do that? Well, for instance, a way to exclude that theory from the cutoff is to start off with energy degrees of freedom that are below the cutoff and exclude any coupling between low energy degrees of freedom and high energy degrees of freedom. So if this is the cutoff, I begin with, my states in the Hilbert space are here. And to make sure that I remain in the Hilbert space, with momentums that I can deal with below the cutoff, I must take away from the theory any component that will couple this, that will make a state here go into a state like that. For instance, an interaction like this, right? Like the one that appeared in second order perturbation theory was doing exactly this. The delta was coupling a low momentum state with an arbitrarily large momentum state, and which I did not know what to do with. So the way you remove this coupling is by regularizing the interaction. How? In the following way. You have your potential. First of all, you Fourier transform it. And then, you anti-Fourier transform it. You're kidding me. Of course, if I Fourier transform something and I anti-Fourier transform something, I get exactly the same object, right? So I'm doing nothing. Of course, this cannot be the end of the day. But when I anti-Fourier transform it, I do something more. I say, this momentum integral will not run from 0 to infinity. It will run from 0 to the maximum momentum I can claim I can control theoretically, because above that momentum, I have no experimental information. So I put a cutoff in momentum integral. That's one way of regularizing. You can regularize in positions as well, but that's more tricky. And there's many ways to do that. You can use a hard cutoff, for instance, restricting literally the momentum in a box, or you can put a Gaussian here that's called a soft cutoff with a characteristic momentum scale here. The result will be the same. It's going to do in a smooth fit way or in a stepwise way, doesn't matter. As long as you're excluding from the theory high momentum. And as you can see, this integral will not receive any contribution from momentum much larger than lambda, the cutoff of your theory. Okay. So in the case of the momentum potential, let's do it. I say have my model momentum. So what do? I do the Fourier transform. Sorry, guys. The Fourier transform, the anti-Fourier transform, sorry, of the Fourier transform of the Coulomb potential. And I put a cutoff here. So if so, formally speaking, this corresponds to taking, let's try to do this. So the Fourier transform of the Coulomb potential in 3D is 1 over q squared, q, 1 over q squared. So so this is going to be the 3p 2 pi to the third e to the negative p dot x 1 over p squared. Okay, so sometimes I use x, sometimes I should use r. I'm a little bit of a messy guy. But then what I do, I put a regularization here. Well, depends how you do it. Let's say I do it with p squared over 2 lambda squared. And I call this v lambda. Now, if I use this v lambda, now, you can even, if you evaluate it, you discover that, this is a, it even has a nice analytic form. And if you look at the lectures in Lepage, you find an analytic form of this, but it never minds. From a mathematical point of view, it makes perfect sense. So that's what it really is, the Coulomb potential from this point on. If lambda is my cutoff, then of course, I should not put anything below the cutoff. Of course, but why did we use the Coulomb potential when we studied the hydrogen atom until today? And the answer is because I was implicitly assuming that the cutoff was so much higher that putting this did not produce any particular effect in all the observables I was looking. Because by the time this term becomes important, I'm looking at short distance physics, so short distance physics that I have to worry about nuclear physics. And normally experiments that do deal with atomic physics don't care about Fermi distance. So the hydrogen atom is good enough in the form that we learned it. So here we have excluded this, but of course we have to do the same with short distance physics. So we need to do d3p 2 pi to the third e to the negative I p dot r, and then the repulsive or the short distance core, Fourier transform of the short distance core, sorry. And then we put our cutoff. So the first step of building a correct theory corresponds to excluding from the theory all the information we have no control on and retain only in the theory the information we have full control and therefore we can trust. Is this clear to everyone, at least conceptually?
Yes.
Yes.
Okay. The second step is the real difficult part, if you want. Because you see, in order to build a theory, we say we need to have full control of the infrared sector. Fine. But then we have this problem that although we could not resolve this physics, there was this new physics. We knew there was physics in the short distance limit because we could not predict the right spectrum just with the infrared physics, right? So there is short distance physics. So how do we write a regularized short distance physics? So here comes the idea. So here is our cutoff. And remember, we are only interested in the infrared sector of the theory. So we want to understand the physics much below the cutoff. Suppose we want to do this. So now, in other words, maybe I should say this. It's a bit late, so probably I will go over this point again next lecture. But let me say it once, and then next lecture I pick it over. So far, up to this point, all we did was exclude from the theory anything that is above the cutoff. Okay? Now, it's up to us what we want to do. We can set ourselves different challenges. We could be very ambitious and say, we want everything. What is everything? Is to be able to predict all phenomena at all scales all the way to the cutoff. We want a full theory that explains all of the experimental data we have until we have it. That's the analog of a standard model. That's one goal. Well, in this case, there is no short way. You need to make so many experiments that eventually you nail down exactly what is the form of the short distance core that we are not knowing. You have to make tons of experiments so that basically you're sensitive to the tiny, you make a huge number of guesses, and then you start validating and you go to conferences and you argue. I say that's the cosine. No, I say it's a Gaussian, and then somebody says it's a Wigner function, and you make theory, you look at data, and after 10 years you come out that we all agree that if you took a Lorentzian factor, hardcore, maybe you explain all the data all the way to the cutoff. That's one option. That's a very ambitious one. In this course, we're going to look at a different option. And it says, I'm not interested to understand everything all the way to the cutoff. I'm interested in the infrared sector only, in the slow dynamics. You have been experiencing this already in your background. Sometimes during your second year, likely, you studied electromagnetism. And in the electromagnetism, you were interested in understanding the electric field produced, say, by an arbitrary charge distribution. And you can do it in two ways. The full glory way is to solve Maxwell's equations for electrostatics given a density. So you really have to solve the Laplace equation in full glory. Good luck with that. You can do it numerically today. Or you could say, I don't really need that because I'm never going to be as close as the size lambda. I'm going to be interested in the electric field much far away from the source. I get an infrared scale R, and my cutoff scale is the size of the charge distribution. And I'm not interested in the details of the physics at the scale lambda. I'm only interested in the detail of the field on the properties with low resolution power, a large distance from the source. And in doing this, you very rapidly converge to the multipole expansion, right? And in the multipole expansion, you can handle this And what is the multiple expansion doing? Is throwing all your unknown ultraviolet physics, the amount of charge, the difference, the dislocation between positive and negative charge, the geometry into a few effective parameters. The monopole charge or the charge, the dipole moment, the quadrupole moment, and so on and so forth. Now, if you know this, all of your very high energy detail of your charge distribution, which is infinitely dimensional information because it's infinitely many points. If you want to infinite resolution to determine a charge density, you need to probe it in infinitely many points. So it's a huge amount of information. You condense it into a set of coefficients. And if you determine those coefficients either microscopically by making calculations or phenomenologically by measuring a few experimental points, then you can get an accurate description of the large distance physics. But here's the catch. For any desired accuracy you want to get, you only need a finite number of coefficients. Right? You want the field to 1%. Maybe you go away quite well with a dipole. You want it for 1 per mil, you need a quadrupole. You want it for 1 per million, you need the octupole. The more you want, the more points, the more effective parameters you need to specify. But to any desired accuracy, you only need a finite set of parameters. So we are off to set ourselves this more modest goal. We know there's a gap between the physics we want to deal with and the possible roof where possibly new physics sets in. I have no idea. I don't care because I'm interested only in the infrared dynamics. And everything that is hidden in here will be mirrored by a few effective constants. Typically, they are dimensionful. Okay? We want to do this for our potential. But let me already anticipate, and I will go back to tell you that that's exactly what we do even in the most fundamental theory we have, the standard model. In the standard model, we don't know the physics at the 100 million teravolt scales. We're interested in the physics at energy much lower than that super cutoff. So whatever happens in the super high energy scale will be reflected by a few constants in the more low energy models we have. And what are those constants? In the electrostatic case, they are the charge, the dipole, the quadrupole. In the standard model case are the charge of the electron, the mass of the electron, the mass of the quarks, and so on and so forth. These are effective parameters that parameterize whatever is up there above the spectrum. We have no way to control it. And we put it in a certain number of constants. So even in the standard model, fundamental theory, it's an effective theory, and the parameters of the standard model are some expansion parameter, just like the dipole, the quadrupole, coefficients of the multiple expansion. I hope I did not disturb you too much with this sort of bringing the gods to the earth and say there's no God in terms of physics. There's only effective theory. But that's everything that people have been able to do so far in science, effective theories. So I will stop here for today unless there are questions. I take in question for a few minutes, and in case we continue with the discussion next time. Are there questions?
Yeah, I have one.
Sure.
Following the line of reasoning is okay, so everything's fine. But when you were explaining the fact that we should have chosen the delta function and we have problems, my naive assumption of what would have come next would be, okay, let's throw away the delta because we know that it is unphysical. Let's try something else, and maybe we can try a Gaussian because the delta is an approximation of the Gaussian. And if we were to do this without the insight above the scale of the theory, we would have ended up with a potential with an effective cutoff of our delta, but without the cutoff on the Coulomb potential. Is this the difference of the insight that we had on the scale?
You made a very good point. I would say from the, can you shut off the microphone because there's a return? Okay, thank you. So we're going to go through this. Okay, next lecture, we do exactly this. You'll discover how smear delta naturally arises from what we just said, if we assume that we are only interested in low energy dynamics. So if you do this, I'm interested in large distance physics in electrodynamics, you naturally have the multipoles, okay? And if you have, if you do, I'm only interested in large distance quantum mechanics, you naturally have smeared delta function and derivative of delta functions potentials, okay? So these are not only we will understand. So what is the next insight? On the one hand is that we need to renormalize the Schrödinger, the Coulomb term too, but that will play very, very little role. The real insight is how to build a rigorous series for the terms we do not understand, for the hardcore terms. And what we will discover that the right way to proceed is to write this as a constant times smear the delta function, where this is a parameter to be fixed, plus second derivative of smear delta function. So it's the second derivative of the Gaussian, if you want, or any function that has a smear, plus fourth derivative of a Gaussian, and so on and so forth. So a derivative expansion. There is nowhere in phenomenological models that you can guess the structure of this. But what we're going to do, these are called the counter terms. What we're going to do next lecture is to show that they naturally emerge from the argument we have given, and they give you a recipe to build a theory without having to guess anything. Just follow the recipe because it's the only sensible thing to doing that is consistent with our assumptions. So basically it reduces your creativity, if you want, from a phonological model where you guess the delta to the only thing you can possibly do, fit these coefficients, because there's only one multiple expansion and there's only one hardcore expansion for a potential. Okay?
Yes, sure, fine. It's clear now.
You will discover that next lecture on Thursday. Okay?
Okay.
Anything else? Well, if not, thank you for sticking out so long. I will now recommend, I will start between 4:30 and 4:35 at the maximum next Tuesday. But I'll see you on Thursday. Okay?
Okay.
Read Lapage lectures. They're wonderful. They're much better than I can possibly give them. Okay? They're really easy reading. Really easy reading. Okay. Bye-bye.